Hello, welcome. In this new video we are going to study some examples of factor groups or the quotient group. Further, we consider the set of integers z as the group G. Addition is the operation defined on z. Z is equal to G. Here we take G equal to Z, and H is equal to 4Z. The subgroup H equal to 4Z, it can be proved that this subgroup is a normal subgroup. So the normal subgroup is 4Z and Z is the original group. We then define, but here the operation is addition. Okay, we define 0 plus 4Z. Then we consider 0 plus 4Z equal to 4Z, because 0 when added to the elements of 4Z, you know that there is no actually no effect. We are going to get trivially the set for Z. Next we consider 1 plus 4Z, where 1 belongs to the set Z of integers. So 1 plus 4Z, then we can see that. So considering the elements, since 4Z contains the elements, see, prior to discuss that, prior to coming to this discussion, we want to see what is 4Z, or what are the elements of 4Z. 4Z contains the elements 0, plus 1, plus 4, minus 4, plus or minus 4, plus or minus 8, etc. Plus or minus 8, then next element is plus or minus 12, and plus or minus 16, etc. Due to this, when we take when we define 1 plus 4Z, we get that the elements are minus the elements are 1, that is the 1 the first element is 1, and then 5, 9, etc. And there we have a sequence. It's going to the positive direction of the real axis. These elements are 1, 5, 9, etc. So you can see that a gap of 4 digits is the integers is in between between two adjacent integers. So 1 plus 4, 5, 5 plus 4, 9, etc. 9 plus 4, the number is 13, etc. It goes like that. Not only that, there exists negative elements, negative elements, minus 3, minus 7, minus 11, etc. All these belong to the set 1 plus 4 is. In a similar way, we can find 2 plus 4 is that contains elements minus 6, minus 2, etc. Then etc. Then we have 2. On the other side of the real axis, on the positive side of the real axis, we have 2, 6, 10, etc. So these are the negative side. On negative side, these values are on the positive side, 2, 6, 10, etc. Okay. The elements of 3 plus 4 is are minus 5, minus 1. How do we get these elements? By adding 3 to all elements present in 4Z. We get the elements in this whole set, minus 5, minus 1, etc. Then 3, 7, 11, etc. And 4 plus 4 is actually it's equal to 4Z. 4 plus 4 is equal to set coming from minus number from minus infinity up to minus 4, 0, and then extending to the positive direction of the real axis, we have 4, 8, etc. Indefinite it goes. These are the elements, but actually this set is equal to 4Z. Okay, thus simultaneously it acts as okay, then 4 plus 4 is what happens to that is, since 4 is an element of 4 is 4 is a member of 4 is see, immediately it becomes equal to 4 is okay. Next we now we claim that there are no other elements. Okay, after describing all these elements, all these special elements, which are the candidates of the set Z bar 4Z, and we show that there exists no other element. If there exists, if you try to define an element which is different from all of these, you can see that it is impossible. You can see that all those elements will become any one of the, it will merge with, or it will coincide with one of the four elements which are described here. The first is 0 plus 4 is z, then 1 plus 4 is z, 2 plus 4 is z, 3 plus 4 is z, and these are the four elements. See, 4 plus 4 is z is nothing but the element 0 plus 4 is z. Okay, for that, but we want to show that, or we want to establish that there is no other different member. So for that, if k, we take an integer k belonging to z, that means we take an integer, then k can be written as, that integer can be written as 4q plus r. Yeah, clearly it can be written, any integer can be written in the form 4q plus r, where q is a suitable integer. Q is a suitable integer and is also an integer, but that integer must satisfy the condition 0 less than or equal to r less than 4. So r is a number, r is the remainder actually. When we divide k by 4, first we do one thing, we can divide k by 4, then we get the quotient q, and the answer we obtain q, and the remainder is obtained r. So we can write k is equal to 4q plus r, where 0 less than or equal to r less than 4. Then k plus 4 is z. We take k plus 4 is z, and that becomes 4q plus r plus 4 is z. And you know, 4q is a multiple of 4q is a multiple of 4, so that can be mixed with, that can be combined or can be diluted, or 4q, the effect of 4q will disappear when it acts with 4 is z. So this 4q, the effect of 4q, the number 4q will be we can see that it will be vanishing. This part will be vanishing. The 4q will be vanishing when it is operated with 4 z, and thus there remains only the number r, hence we get that it is equal to r plus 4 z. But this r is some number from 0 to 3. R is either 0, 1, 2 or 3, and that is clear. That is clear. That was already in that range of variation of r is mentioned here. Therefore it can be either 0, 1, 2 or 3, and hence it is clear that no distinct no other element can exist which is distinct from the four of the elements which are described here. We can prepare a table that is called a KD table using this information that we have that we have here in our past discussion. So, and that information can be summarized here in a table. See, you can see that rows and columns in the table. In the first column, you can take the elements 4 is z, 1 plus 4 is z, 2 plus 4 is z, and 3 plus 4 is z. In the first row, that is the label row. Labels, these are the labels in that row which are taken in that row. 0 plus 4 is z, 1 plus 4 is z, 2 plus 4 is z, and 3 plus 4 is z. So using these two row wise and these labels or the names column wise and row wise, you can add them. See, by adding these two elements you can obtain the number 0 plus 4 is in the first cell. In the body of that table we can find there exists empty cells, and these values can be determined by operating the elements here in this column one by one, operating the elements in the column with the elements which are available in the row, in the first row. So as some examples, see, you can operate 0 plus 4 is with the 0 plus 4 is operation is addition. You can add these two elements and obtain that the answer is and you can write the answer here in the first cell. 0 plus 4 is it, but 0 plus 4 is when added to 1 plus 4 is can give us 1 plus 4 is when 0 plus 4 is added to 2 plus 4 is we get 2 plus 4 is. So in this way you can completely fill that main body of the table, and this is called, once again I would like to say that this is called the Cayley's table. Okay, therefore from this discussion we it is clear that Z bar 4 is that group, the quotient group Z bar 4 is it behaves like it behaves exactly like the group Z4. It's because there are only 4 elements, and also these 4 elements shows the behavior of the data, behavior of the exact behavior. It shows the behavior which is exactly that of the behavior of the set Z4. This Z4 is a group that you are familiar with. Okay, that also contains 4 elements, and addition is the operation defined there. Those elements are 0, 1, 2, 3. These are the elements. 0, 1, 2 and 3 are the elements, but when you try to include 4 there, that becomes the element 0. Okay, then you can generalize this concept. This is the concept. It's a concept which is explained in the case of Z and its normal subgroup for Z. You can generalize this concept in the case of NZ. Okay, where n is any natural number greater than 0. So considering the set of integers Z and taking the number instead of 4 by taking n where n is any natural number, and we get that Z bar NZ is isomorphic to Z bar NZ can behave exactly like Zn, the group Zn. Okay, and that means they are isomorphic. There is no distinction between these two groups, or this group behaves like that the group Zn, and the group Zn acts like the group Z bar NZ. Okay, we have one more example here. Okay, and that example tells it's about Z18. Okay, that we take G equal to Z, the given group. We take Z18 as the given group. At the price of G, we consider Z18, and the normal subgroup. We require a normal subgroup. That normal subgroup H is equal to the cyclic group generated by 6. So Z18 and the cyclic group generated by 6. Clearly, this is a subset of the Z18, the group Z18, and also it's a subgroup. Yeah, it's also a normal subgroup. It's also a normal subgroup. Then okay, the elements of 6 of the cyclic group generated by 6 are 0, 6 and 12. It's clear. 0, 6 and 12 are the elements, and here 0 is the anti-element. So let's think about G bar H. That quotient group, the G bar H is equal to 0 plus H, where H is the group, the cyclic group, and then we can write 0 plus H, 1 plus H, 2 plus H, 3 plus H, 4 plus H, and 5 plus H. What about 6 plus H? 6 plus H is not different from 0 plus H. So now any term written after this point will be one of the elements already we have included in that in the non-empties in this set. Okay, therefore no need to consider all those remaining elements. And we define the operation. We want to conveniently define an operation here. So for that, see, as an example, an operation is defined here. Here it illustrates this line, or this step illustrates the definition of an operation. So 2 plus h is an element. This element is taken, first element, and plus. So it should be nice if we use a bracket here to put these two, or write these two terms together. So by using bracket, you can conveniently use brackets to write, to give us the feeling, to give the reader a good feeling that these two elements are belong to a single element. So these are not two different elements, it's a single element. Okay, so this single element plus the second single element, that is 3 plus h, so that can also be included, can be put in a bracket. So they can be combined to give us 2 plus 3. See, these two numbers can be added, 2 plus 3 plus h, that is equal to 5 plus h. So this way very clearly we can define the binary operation, and also we can show that binary operation is well defined. Okay, and you can say that, you can point out that this is 0 plus h is the identity element. 0 plus h is the identity element in this case, and of course every element has an inverse. You can find inverse for every element. That, for example, 1 plus h, the inverse of 1 plus h will be 5 plus h, and inverse of 2 plus h is 4 plus h, because adding 2 plus h and 4 plus h give us 6 plus h, that's equal to 0 plus h. That is the identity element in that group. So every element possesses an inverse, and finally you can easily verify that associativity property of the binary operation is also satisfied. Hence this is a very good example for a factor group. Okay, at this point I want to stop. So thank you.